And welcome. We have proved that there is a correspondence between all the subgroups of G and all the intermediate subfields of this Galois extension E or F. So now the question is, are all these intermediate subfield extensions are Galois or not? So the answer is no in general. So we know that this is Galois extension. So all the intermediate extensions will be separable, but the normality is not guaranteed. So it will be normal extension only when associated Galois subgroup is normal. So that is what we are going to prove here. So let L or F be a normal extension. Then since it is intermediate field extensions and it is normal, we know that it is already separable. So L or F will be Galois. So now we define a map from G of E or F, which is Galois group of E or F, and to G of L over F. Okay, so since it is Galois group, so this group is well defined. So and it is defined as phi of sigma, which is element of E or F, is equal to sigma restricted to L. So we know that L is a subfield of E. So this map is well defined and it is onto. So it is onto homomorphism. You know the by first theorem of group isomorphism, that G of E or F mod kernel of phi is isomorphic to G of L over F. So what does meaning of sigma to be in kernel of phi? That phi of sigma is equal to identity. What does that mean? That sigma restricted to L is identity. What does that mean that sigma restricted to L is identity? It is all those group automorphisms which are restricted to L and with fixed field F. So what does that mean? That sigma belongs to G of E over F. So what does that mean? That G of E over F mod G of E over L is isomorphic to G of L over F, and G of E over L is a kernel here. You know that this is kernel. So G kernel of phi is equal to G of E over L is a normal. So we know that kernels are normal. So we have proved. So for the converse, let G of E over L is normal in G. G is G of E over L. So we can notice that since it is normal and this is H, so sigma H, sigma inverse is equal to H for all H, and L is a subfield. L is a fixed field, and we know that L is a fixed field of H. So this both sigma H, sigma inverse, and H will have same fixed field. So consider L dash be the fixed field of sigma H, sigma inverse. Then what will be meaning of element A to be in this fixed field? So A will be basically element of E, which will be fixed under this subfield L dash. Okay. So what does that mean? That sigma phi, sigma inverse of A is equal to A for all phi in H. So if I apply sigma inverse, then phi sigma inverse of A is equal to sigma inverse of A for all theta belongs to H. But what does that mean? Then theta of sigma inverse of A is equal to, so this theta means what? It is fixed by all the theta in H. So what does that mean? That this sigma inverse of A on right hand side will be L, because L is a fixed field of H. Okay. So since its inverse goes to L, sigma A will be goes to L. And what does that mean? That it is element of L dash. So L dash is equal to sigma of L. And that proves that this proves the sigma of L is equal to L. So we know that there is this is the for normality there is a alternative definition that every fixed you know that there is theorem that if E or F is a normal extension, and then every F automorphism sends L to L itself. So that is what we have proved, that this sigma is any automorphism from G, and it sends L, means the fixed field, to L itself. So that is what we have proved. So therefore L over F is normal extension. And we have proved this theorem. Thanks for watching. And this is end of the fundamental theorem of Galois theory.